Good afternoon. This is a video about the construction of my aerial photos website, wingvista.org, the technology that it runs on, and an overview of some of the places over in the UK I've flown over and are represented on the site in a series of 360-degree photos. I'm Neil Miller. My main hobby is flying. Here's a picture of the aircraft at Oxford Airport. We own it, me and 3 others own it. And we keep it a farm airstrip in there and over in Hampshire. Part of the fun of flying, I think, is seeing the world from the air. So, like many pilots, I would take pictures on the phone, and that starts making me think about ways to potentially automate the process. Google has its Street View service, which we can see here, which consists of a large number of points on all the roads, many of the roads in the UK and worldwide, where a Google van has driven, taking these photos. So you click on there, and that shows what is visible, and you can click forward and go backwards as well. So good quality 360-degree photos. So I had an idea. Why not lift Street View up into the sky? Now, you certainly were able to upload your own images onto Google Street View itself in the past, but I thought they would probably not accept content from the aircraft for the simple reason that would show on top of their existing content for roads and cause the users inconvenience, where the user wants to see what's on the ground and end up getting a picture from 4,000 feet up in the air. So I knew I would have to write my own website for it as well. So I purchased one of these, a Samsung Gear 360 camera, attached it to one of these, a Rocksteady mount shipped in from the United States, and one of these, a second Android mobile phone, and of course use my aircraft, and got coding. The phone itself has the Google Street View app on it, which we can see here, but when it's running and attached, it basically looks like this, not much to it. And I'll put that down there, and then we've got the camera assembly, which we got here. This attaches to the strut of the aircraft and hangs down like this, and communicates with the phone over Wi-Fi. It's got a Wi-Fi connection. So if I click here, it starts collecting with that beep indicating it's taking a photo, and it downloads the photo to the phone over the next few seconds. Put that down there. Beep. Here again, that's the next photo that it takes, and it records the GPS location on the phone as it goes. 6 years later, after doing all this, and after spending far more time on the project than was sensible, and after collecting footage from my flights all over the south of the UK, I had a version of a website that I was happy with, and I've called it Wingvista. So if we Google it, it's got a slightly obscure name, which ensures that it's top results. It was top result on Google, and here it is. It's a background map using OpenStreetMap technology, and we can see a series of blue circles with red lines running along them, each blue circle representing a photo that's been taken. So if we click on one of them here, and it's a 360-degree photo. If we turn it round, initially here's your intrepid pilot flying the aeroplane, and as it's a 360 photo, we can see basically everywhere around here, and we can zoom in as well. Each image is got about almost exactly 8 megs in size, so we get a decent bit of detail on here as well. Then when you scroll up, we've got the 3-way toggle button, which takes us to the third view, which is the information page, which gives us metadata about this particular image we've got selected. So the time here when it was taken, so this was taken on the 26th of June 2020 during the time of COVID at 17:37 and 55 seconds. This tells us that the altitude in feet is 2,000 feet above sea level. QNH is an aviation term that denotes that. Rate of ascent, descent of flying exactly level, which is actually slightly unusual. Normally there's a slight rise and fall. I should say this this altitude is picked up by another app which I'm running on my second phone, which records the altitude and saves it into a file on that second phone. And I got the ground speed in knots, so this time I'm doing 110 knots, quite fast. The average speed is more like 80 knots, and which is about 140 kilometers an hour, maybe 150 kilometers an hour. And this one here, open this location in Google Maps, opens the location here, as we can see. So if we scroll down into it, we know this particular flight. If I just go back to the image there, we can see here this little plane icon has appeared, showing the direction in which the aircraft's travelling. It's over the top of the town of Godalming in Surrey on this occasion. So if we let's go back to here again. If I zoom in, we can see that there's this straight ahead to the right of here. We've got this slightly sort of rectangular field shape, and then Godalming railway station just beyond that. So if we go back to Wing Vista, click on the toggle, I'll just come out of it, and then let's look where, so that's the forward direction. We go back to the forward direction again, and go down. There we are, and we can see pretty much that if we turn it, you can see where the nadir is. That's the place directly underneath the flight. It's about here, and we can see this same rectangular shape of field here, and then a bit beyond that you got Godalming railway station here. So it works. So the location recorded on that map is actually where I am. The next question is, how do we collect footage for the site and load it into the system, and where does Node.js come into it? Simplifying a bit, there are 4 stages to the generation of a website. Although the live site runs on Amazon AWS with the image files in S3 buckets and served out with Amazon CloudFront to allow for HTTPS. Here I'm connected onto my dev server, which I'm running in my spare room in Hampshire. So obviously we do the flights to collect the photos, and they're geotagged with the image location. And they are saved initially onto the Android phone I showed earlier. Initially copy them over USB to a new directory on the server. And here is an example of the image. There's an example image taken. Make it slightly bigger there. So it's about 8 megs in size, so it's quite detailed. This was a flight to Gloucestershire. That's GCHQ on the right hand side here. The slightly weird format is called equirectangular, and it's how 360-degree photos are stored in a format that is readily viewable in regular image editing software. The display software that displays it on a website in the 360 format reformats it on the fly. So the file itself, as I said, is date time stamped, which we can see here. This is the original naming format. Pano is panorama, 2023, April 25th, and the date time there. And it's geotagged with the latitude and the longitude, which is saved onto it with a phone, which we can see if we bring up the Windows properties for the file. Under the details tab here, if we scroll down, we get this latitude and longitude information. This data is subsequently extracted into actually empty files with the latitude and longitude and the file name by a command line utility called exif tool. Incidentally, very often when you take photos with your regular smartphone, that location information is saved into the file as well, and that by uploading the photo to a photo sharing website, there's at least a possibility that this information will be uploaded as well. I don't know whether this is the case with popular websites like Instagram. And if a photo is publicly viewable, then theoretically anyone can access that data and work out where you live, for example, if the photo was taken at home. This happened in an episode of the police procedural drama, a documentary really, 24 Hours in Police Custody, where a doctor was caught out for insurance fraud when the geotagged location on a photo that he sent in as evidence of the loss of an antique to the police had a geotagged image placing him in a location where he said he hadn't been. So that's that. So after copying, I'll digress a bit, so let's go back on topic. Next, a SQL stored procedure runs, which here's an image screenshot of it, and the actual stored procedure is visible in SQL Server Management Studio here. This runs and processes the data. It basically gets the list of image files, literally does a dir and to output to a file, and then loads that into a SQL table. The SQL stored procedure, after processing, produces a couple of output files, one of which is in the GPX format, which is basically XML, which has got latitude and longitude and other kinds of information on it. And let me just show quickly an example of the GPX. Bellsloop.gpx is a sample GPX file where we can see each waypoint here is basically the equivalent of a photo. This is not from my website, this is from a sample website, but we've got the latitude and longitude values there, as well as the time and other metadata as well. And then is at this point is where Node.js comes into it, because it compiles the core JavaScript, which are written as the main body of a website, into the application. Now, I don't claim to be an expert in this language. My long professional experience is as a Microsoft SQL Server developer and DBA, and I had not coded in JavaScript, or it's not more than 1 or 2 lines at all prior to doing this. As it's my own project with no boss or company to report to, I've very much adopted a redneck approach to it, focusing on what works rather than what's the best way to do it, shamelessly stealing code from anywhere I could, which probably means it's about to fall over completely or get hacked, but I don't care, as I've got it all well backed up offline. To do the compiling of it, it's simply a case of running a Windows batch, which I shall demonstrate now. Here, and run that, and it runs initially the stored procedure call, and then runs the as you can so just get this, move this over slightly out of the way, and you can see here that it runs npm run build. Npm is the command to run a Node.js compiler, which in turn runs runs the stored procedure call, first of all, using this OSQL command line utility, running process wing vista, which is the name of the stored procedure. And then after the Node.js has processed it, emits these various files, and then whinging about some of them being too big, and then puts them up onto the website. So the website initially gets put onto my local server, which I can bring up here. and the SQL. So Wing Vista Dev. So it's present on the local box here, and I've just a little graphic here which helps me to distinguish between the two. Right, so what's the technology in Node.js that allows this to be displayed? The answer to that is it's a technology called OpenLayers, which I should bring up here, which is open source code. Basically, it's a JavaScript library, and it's as its name suggests, it renders web pages by adding layers of detail on top of each other. So a base layer is a tile or raster layer is the map, which we can see the background here. Obviously, the same thing like Glastonbury, Castle Carey. And this data comes from, if I go back onto my server, the way that I've implemented it is as a rather large number of PNG files that I've downloaded. Well, actually, I downloaded a utility to generate these files, and so this one, for example, showing the city of Manchester, and you have other versions where you zoom in, and the OpenLayers software knits what are called tiles, map tiles, knits them together into a map. And then the next layer on top of that is the layer that handles the tracks and the circles representing the photos in blue, which is known as a vector layer. Notice in Wing Vista that the red line itself is continuous. If I said a bit awkward with the small screen, but we'll get there. It's a single red line that goes all over the shop. Unfortunately, at the end of one line, the red line goes to the beginning of the next track. So you've got these slightly unsightly red lines which crisscross the place, which at some point I'm going to try and get rid of. So that's the vector layer, which has the circles, and each circle is encoded with the metadata corresponding to the individual photo and the corresponding flight information. And the final layer, the third layer, is the red icon for the aircraft, which we can see there. Let's take a look at how this is implemented in the code. I started building a website on top of a demo code for GPX-based websites on the OpenLayers website, which is here. This has a similar sort of thing as you can see how it formed the starting point for Wing Vista, namely a map background. Although this is a satellite view background, it is the same principle of lots of image files going steadily into more detail as you zoom in. And this the tracks here and these particular points here. If we scroll down into the code itself, the main bit of code here is the definition of the variable map, which is defined as a new map with a capital M, which itself is defined up here. Map is loaded in from openlayers.map.js, and this new variable that we defined has properties, two layers on it, raster and vector, which is a map and the vector representing the track and those points. Where we can, each point is what's called a waypoint. We can see that if we scroll up slightly, we can see here that the map raster in this case gets its data from, in this case it's a URL call from an external API, maptyler.com, whereas on my version it pulls it from a local directory, but both seem to work fine. And the vector layer is here. That reads its data fundamentally from this GPX file, Bell's loop, that I showed you a short while ago. And then when we've got this map.onClick function, which does stuff every time you left click on the map. So it runs this function called display feature info, which grabs the metadata associated with the object at that particular point. In this particular case, corresponding to one of these dots here, and in fact, this particular example has got, if you see the bits of text changing on the bottom left of the page, that occurs just also as a result of doing a mouse over that particular point. But that all gets done by the function call. So looking at my code, if we jump onto the server, oops, move this out of the way slightly. My code's in Visual Studio Code, and should move this completely out of the way so it's not getting in the way of anything. There's about what's turned out about 1,000 lines of code, and so the corresponding bit is at line 857, where the variable OMAP, as I've called it, is of type new mod map, where module map is defined at the top here. Line 5 as loading in from OpenLayers map. In fact, it's loading from map.js, which is a locally installed driver file for the OpenLayers software. So go back to line 857, my code, and we can see that, like in the example, too far. Like in the example, we've got 3 separate layers: OLayer background map, which is a map; OLayer vector GPX, which is the tracks and the circles; and then a third layer just representing the icon for the aircraft. So looking at these 3 in turn. So OpenLayer background map, if you search for it, that's defined at 177. So here we can see that it's pulling the data locally rather than from an API. That seems to work just as well. Then I did try to get it working as an API, but couldn't for some reason. So I found that it did actually work as a local file call, so I haven't changed it. In theory, you can use smaller files than the JPEG files, and I've got several gigs worth of those JPEG files. You can, in theory, have a bit of software which reads them and generates the image of the map tile data on the fly, but I don't believe I was able to get that working. Then the next one is the OpenLayer vector GPX, which is just next door here, and that is referencing this departures.gpx.txt file that which is a GPX file that which the SQL Server stored procedure outputs from the data metadata of the image file after being processed. And then finally at line 169, it adds a layer vector aircraft icon, 169 here, which is a small red aeroplane, which is defined on line 187 as having style aircraft icon here. So I'll just do a search here, you should find it, which the OpenLayers property of rotation is given to it, which rotates it clockwise. It takes as input parameter of heading of the aircraft, which we saw over, which is as part of the map. If we click on here, now we've got this heading, in this case 72, and go back to this code here, and it takes that which is read as a floating point number heading, and it multiplies it by 0.0174, which is approximately 2 pi over 160. Beg your pardon, 2 pi over 360, which converts it into a unit of rotation, or angle I should say, called the radian, which some of us may remember from school. Now, if you're an aviation purist, you'll be about to tell me that the aircraft actually probably wasn't pointing. If we go back to the aircraft here, there we are. It probably wasn't actually pointing in the direction shown, because it was likely to have, the aircraft was likely to have had to point slightly into wind, left or right, port or starboard. But I think it would have been a step a little bit too far to record the actual bearing of the aircraft as opposed to the heading. Though I dare say there is a smartphone app that could have allowed me to do this, but I thought that was really not a sensible use of time. So let's click on the circle and see what happens to make it display the photo. Right, so in the normal way, when we click on one of the dots, we get the image. What happens in the in the source code? Move this out of the way. It calls this function render image with the image sequence number that uniquely identifies which image. And it initially populates these variables here, pulling data out of data that has been loaded into this string called simageInfo. simageInfo comes from the compiled, this file here is the compiled version of main.js, and this data is also present in the source file, one of the two source files that is provided to the compiler. And this string, it basically contains all the metadata in a single string with letters showing whereabouts in the string the data is. So, for example, here we've got the time the image was taken, excuse me, the height. I think the height is actually in meters rather than feet, but it gets converted on the fly. Rate of climb, of descent, latitude and longitude, speed in knots, etc. And the heading. And there's one of these rows for each photo. So basically the code oops, go back to my virtual machine here. The code here breaks out this information into variables. So we scroll down here, does a bit of processing, and what it at this particular point, it constructs the string that goes into the web page for the information. So it shows the altitude, etc., on the information page. And then finally, the viewing of the image itself, and it uses this software called Pannellum to view the image with various parameters, including the image path and the way the image gets displayed. The software, the Pannellum software, only needs to be installed on the compiler machine. You do not need the software on the local web browser to view the image. So Pannellum, if I go back to my local machine, is here. This is a website for Pannellum. Get rid of this again, and we can see that this is and it's and then software, which is here. And there's a particular place that I want to look at, so let me zoom in on that now. So we click on here, and we've got our image. It's got several parameters like pitch and yaw that are up here in the URL. So if we change, we can change some of these parameters. For example, image yaw 5. We change that image yaw 90. It turns the image around, and the opposite is the case as well. If I move the image around, the values in the URL change. So what that means is if we want to have a particular view that's encoded into the URL, I can email it to someone. They can open it up in a browser, and it opens up the same thing. So there's no ambiguity. It's easy to say to communicate from one person to another what you happen to be looking at. And that's all done. By reading the URL parameters and writing them into place with this Pannellum viewer function call. Just as an aside, there are two ways that the image can be displayed. There's the yaw, which I've already shown you. Then you've got the image pitch. If I change that into +90, for example here, that's looking straight up. But there's also another method if you want to. There are two other parameters that you're less likely to want to access. The images themselves, at the moment, the image itself is the axis, if you like, here is pointing straight downwards, but you can change that axis so that the axis is straight forwards or at some angle, and you can do that in the parameters here that get fed through to the function call. If I can get to it, image horizontal roll, for example, if I change that to 90, you get this. And this looks kind of doesn't look terribly useful. I think most would agree that this is not the best way of displaying it. The same with the image horizontal pitch as well. You can also break that in the same way. What does that do? Well, it's completely broken. So that works quite well. So that basically completes the fundamentals of it. There's two other points. There's a bit of code, oimage add event listener here, which is what's responsible for picking up when I drag it and putting those changes it's down here. There's a number of them. Add event listener, which pick up the clicks and the movement in the image and get the parameters and save them into the application. There's another one. If I go right to the end of here, there's a bit of code here credited to Wang Chu, some presumably Chinese gentleman or lady, which allows you to use the up and down arrows to move forward and backwards. So if we click forwards, come back there a bit. So if we go forwards, it goes to the next image along, and so on like that. So it gives the impression of going forwards and backwards as it accesses those different images along the line. So that's basically the application. There was a particular problem to do with location, to do with a delay in the GPS location recorder, which I'll demonstrate here. Go back to the where we were, and I'll just go on to this one here. If we look on the map, we can see that there's, we'll zoom in a bit further. We go to the image and go straight downwards, we can see that we are roughly here, and that's just to the right of the Y shape of the road here. The road goes up to the right, road goes off to the left here and down. So we're about here. But if we look at the map, we notice there's the Y-shaped road, but the position of the aircraft is quite a bit forwards here. And the reason for that is a problem with the Street View app, which is that it waits until the photo has been downloaded over the Wi-Fi from the camera to the phone before it reads its current GPS location and saving it to the file's metadata. The problem, of course, is over a few seconds that occurs, the aircraft has moved a few 100 meters further forwards. So how did I fix this? And this is where the date time of the photos come into play. So looking at that, if we go back to my local machine, I've got some screenshots. So, excuse me. Here is the thing with the 2 dots there, and this the top dot here representing the incorrect position. If we go to here, we can look at the toggle. We can see that the time this was taken 16:08:08. So and the previous put the 2 times on 16:08:08, and the previous picture was 16:07:44. So the way to solve it is to create a second virtual time for the photos, which is equal to the original time minus X seconds. And then what we do is use the length between the 2 dots to calculate a virtual location for the photo as a ratio of the 2 times. So now I already know that the offset, the difference, X is minus 8 seconds. So we'll put that on here. So we know that the correct location is here, and I happen to know that the correct value is 8 seconds back from 16:08:08, which is 16:08:0. And then it's just a case of working out the latitude and longitude of a new virtual point. And this is done with a bit of maths from the data we have. We know the latitude and longitude values for this dot and this dot here. So we calculate the difference between the two, which is these 2 values here. And then what fraction of a way back along the line are we? Well, that's the value of X, in this case it's 8 seconds, divided by the difference in time of 2 values, 16:08:08 to 16:07:44, that's 24 seconds. So 8 divided by 24 is 0.333. So time difference. So the new latitude and longitude that we want is the original latitude and longitude minus 0.3333 multiplied by the difference values, and that gives these 2 values here. And although I won't show you, it basically equals the latitude and longitude here. So this is all done. This calculation is all done on the fly in the SQL Server, the stored procedure. Now, the stored procedure I did, I now realise putting together this tutorial that I have actually significantly overcomplicated it because I, in error, thought that it was necessary for me potentially to reference a different waypoint. But I now realise that was simply not necessary. I was being far too generalised in the situation. So this bit of code here is excessively complicated. So I could simplify it in order to do this calculation. And so to fix it, we've got this flight table here with 1 record per individual flight. We scroll down to here. We've got this offset value here, and I simply add in, it's currently set to 0, which means no correction. So change that to 8,000 and save it. And then go down here and recompile it. And in a moment, it will make the fix. It shouldn't take a moment. While it's working. So that's worked. So now we'll go to here and back up to here. And now if I do a Control F5 with a bit of luck, just wait for that to reload in the excuse me, reload in. You might need to just zoom in a bit to make the tiles reappear. Come out a bit. There we are. So zoom in again, and now we can see that the location of the aircraft is now correctly just a bit to the left of the Y shape, which is what we had before here, just by way of a reminder. Yeah, that's about right. It's not perfect. In fact, one thing which means it's not perfect is the fact that if you're turning, then you can't have the straight line, but extrapolation. But I thought that's a detail I don't want to be involved with. I suppose a thought occurred to me the other day. I wonder whether I could maybe use AI as a way of working out the correct location. Take a load of tracks of aircraft flying around the place and use AI. Come out a bit. Feed in the dots, the location of the dots here, and use AI to work out where the aircraft probably was and what kind of turn rate, etc., the aircraft was probably doing. But I'm sure that's just a solution in search of a problem rather than the other way around. So going back to the SQL here. The stored procedure does work out the scroll down a bit if I find it. It works out the location of the things hiding from me. There we are. So in here I work out the ground speed from the time between the two dots and the distance travelled, with the distance travelled calculated by the difference in latitude equal, where 1 degree of latitude is 60 nautical miles, and 1 degree of longitude multiplied by the cosine of latitude to deal with the fact you're north of the equator, also equaling 60 nautical miles, all plugged into this formula here, which you'll recognize, I would imagine, from school. Goes a bit further along there. So that was an introduction to the technical side of how it works. I want to spend the last few minutes showing some of the interesting sites that are on the site. Probably the coolest one, in my opinion, was one I got during COVID, when it was possible to fly over Gatwick Airport. Basically, the airport was closed due to no commercial flights during the time of COVID, and so we can see all the aircraft parked up here. Bit of a sad sight, has to be said. Normally light aircraft would not be allowed to fly in a controlled airspace. It's still controlled airspace, and I have to still call up the controller to get a clearance, but because there's no commercial traffic, there was no reason to say no. So that was one place that I went to. Other places, I've been out to the Far oh, just before I forget that particular one, if we go here, we can see another example of what happened during COVID. If I click on this one here, this is you see quite a bit higher here. What height am I at? About 6,000 feet. Yeah, it's just over a mile high. So yeah, zoom in down here, if I recall correctly, somewhere. This is Kemble Airfield or Cotswold Airport or something like that. These are a load of British Airways Boeing 747. There's another similar aircraft. Again, parked up, and it's rather sad really, because some of these aircraft were never brought back into service and were scrapped. Well, I understand there is a Boeing 747 still at Kemble, which has been opened as a kind of a tourist attraction. This is the one of the suspension bridges from England to Wales. Looks rather nice. And flew into Bristol, and kind of a neat view here on the Clifton suspension bridge. A little bit, oh, it's not too bad, the quality on that. So come out, and Western-super-Mare. Well, this is kind of a neat one. There was a fly into Cardiff Airport, so this is the aircraft on the ground, which I was able to get. Let's just zoom in a bit further, and you can see the final approach path here coming into land. Where else have I been? I've been, come out a bit further, up to the Brecon Beacons. It's great fun flying around these hills. It really does feel, when you're in an aircraft, almost as like you're flying on a magic carpet. The way you're able to go up and down the hills that would, in a matter of seconds, but would normally take you know, half an hour or more to walk on. Go out a bit further. I've been over to the Scilly Isles, there, somewhere, all the way down to Cornwall, which is kind of picturesque. Really look very nice, and I was very lucky with the weather. It's necessary to cross over from the mainland over to the Scilly Isles at a height of about 10,000 feet, 2 miles, so that if the engine quits, you can glide to either side without risk of landing in the drink. And that's Hewtown, I believe it's called, which is like the main capital, which is picturesque because it's got a beach on both sides of it. And let's go along here. Where's the airfield? So there's somewhere. That's on the kind of final approach path there. You got the St Mary's tower there. It's a fully controlled tower there. It's actually a busier airfield than I thought it was going to be. Then we got Land's End, which looks very nice with the here we are, Land's End complex with the cliffs and loads of tourists. I did, as I flew past it, I did waggle my wings from one side to the other to try to get attention, but no one was interested. And I've been all the way over to Dover. This is a flight. There's the White Cliffs of Dover, Dover Eastern Docks there. And if we scroll around here, got quite a couple of cross-channel ferries there. And I'll show you to. So it's fairly fast and responsive. If I click on here, this is about as far out as I was able to get. So that's the north coast of France, we can see, and those are 2 cross-channel ferries. Quality is not the greatest. This is about as far out as I felt comfortable going because it's about 6 miles out. But we can pretty much work out how far out we are if we go to here and bring up the Google map of it, and then roughly right click and say measure distance, and the distance to nearest land is, it's not telling me, oh yeah, about 5.3 miles or so, and the altitude I was at was hiding from me again, about 6,000 feet, so just over a mile high. So it's a glide angle of about 1 in 6, which is a comfortable glide angle. So if the engine did quit there, I would be as sure as I could ever be that I would be able to glide back and land on dry land. Most of my flights have been in and around the Isle of Wight area, just a bit of the north coast of the Isle of Wight here. What else we got? I managed to over Southampton, and where else have I got? Oh yeah, I did Snowdon. Just there, oops, that's Snowdon, and you got the track and the mountain railway going up there, which I think we can see. I think that's a station. That might be possibly a train there, I'm not sure. You can't quite see the people, it's just slightly too small. You're not allowed to travel within 500 feet of people or objects, man-made objects on the ground. And Blackpool, over Blackpool. Blackpool's got a nice airport which you can fly into here, as you can see there, and click on that one there. We see the 3 piers here, and Blackpool Pleasure Beach, which if you haven't been, I would certainly recommend it. With what was at one stage, I think was actually the world's tallest roller coaster, the Pepsi Max big one. Anyway, they managed to get me drinking the stuff. I have a definite addiction to it. Right, enough of that. Thanks for watching. The website is wingvista.org. My name is Neil Miller. For day job, I'm an experienced SQL Server developer contractor, currently looking for my next role. The market's a bit quiet at the moment. There's my email address, there's my LinkedIn. And if you happen to have access to a twin-engine aircraft or helicopter, I'd love to see if we could attach a camera to it and get some footage over central London, because London is, you need to have a twin-engine aircraft because there's nowhere to land if the engine quits.